Still 3 minutes. Facing hospital. Yeah. All right. I think we can start. So good afternoon, everyone. It's a real pleasure to welcome you all to this year's David Olive Distinguished Lecture. And it's an even greater pleasure to introduce our speaker, Professor Edward Witten. Now, I understand that most of the audience consists of colleagues from within the UK and outside, physicists and mathematicians. And of course, Edward Witten needs no introduction to this community. His work has shaped modern theoretical physics and deepened its ties with pure mathematics in ways that are very hard to overstate. From quantum field theory and string M theory to geometry, topology, and knot invariance, he has inspired and revealed to us breathtaking physics while simultaneously demonstrating the power of physics in mathematics. But this event is also about a few connections, and today's lecture has quite a few interesting connections. Edward Witten wrote with David Olive a seminal paper on electromagnetic or electric-magnetic duality in supersymmetric theories, which eventually became central to our understanding of gauge theory and string theory. Electric magnetic duality in QFT was, of course, a concept that David Olive helped pioneer along with Klaus Montoni. There is yet another connection to Swansea. Edward Witten visited Swansea in 1988 and for the International Congress on Mathematical Physics. And as is now part of local folklore, there was this famous dinner at Annie's restaurant one evening with Michael Atiyah and Graham Segal present. And the conversation turned to the celebrated Jones polynomial for knots, which triggered Witten's groundbreaking interpretation of the Jones polynomial using Chern-Simons theory, a result that actually brought quantum field theory into the heart of knot theory and helped him earn the Fields Medal the following year. Now, there is a plaque for commemorating this historic dinner, which is apparently with someone at the Department of Mathematics in Swansea. The fate of the napkin with Edward's arguments remains as yet unknown. It's also fitting that this lecture comes just a day after another milestone. Edward Witten has been named an honorary fellow of the Learned Society of Wales, joining a distinguished list that includes Michael Atiyah and Vaughan Jones himself, with David Olive being a founding fellow of the LSW. And at this point, I think I should thank Professor David Evans of Cardiff University for actually taking the initiative to make this possible. Okay, so this isn't just a talk, it's a full circle moment. It's honoring David Olive, it's celebrating a historic visit to Swansea, and welcoming one of the greatest minds in theoretical physics. So please join me in welcoming Professor Edward Witten for this lecture.
Well, thank you very much for the kind words, even if possibly overstated at times. So I'm very pleased to give a lecture in honor of David Olive. You know, David Olive was very important in my career, both because of the joint paper I wrote with him, which was just mentioned, but he of course was one of the pioneers of the whole idea that string theory could be used to describe gravity, and was one of the discoverers of space-time supersymmetry in string theory. And he also was one of the pioneers of electric magnetic duality, along with Goddard, Neutz, and Montonen in different papers. And that actually, those two papers that I just mentioned were actually the background for the work I did with David Olive, which I think was at the end of 1977. Anyway, my topic today is a background independent algebra in quantum gravity, as you can see. So for a starting point, let's just remember what happens in ordinary quantum mechanics. In ordinary quantum mechanics, we usually consider the observer to be outside the system that's being observed. But that's problematical in the presence of gravity, because, well, most obviously in the case of a closed universe, no one can look at a closed universe from outside, and the only possible observer in a closed universe is an observer who lives in the universe, and thus is part of the system being studied. Another difference between quantum field theory and gravity is that in quantum field theory without gravity, we can pick an arbitrary region, which I'll call curly U in space-time, and define an algebra of observables in that region. So very schematically here, I've drawn M as space-time, and U is a region in space-time, which I've chosen to be a so-called causal diamond. And then we can consider the quantum field, but only restricted to the region U. And that will define an algebra of observables appropriate to that region. There are problems with this in the presence of gravity. With space-time fluctuating, it's in general hard to explain what we mean by the region U. We can't define it by the values of the coordinates because that would not be generally covariant. It only makes sense to talk about particular regions that can be defined invariantly. For example, the region outside of a black hole horizon is an example of a region that does make sense in gravity. But a more fundamental question is, why do we want to define an algebra unless it's the algebra of observables available to someone who lives in the space-time? In ordinary quantum field theory, we can imagine someone outside the space-time who probes it at will, but only in some given space-time region, such as the region U that I've drawn here. In gravity, the person who's probing the space-time is living in the space-time, and it's only natural to consider an algebra if it is the algebra of observables accessible to some observer. So I want to construct an algebra that describes the measurements made by an observer. I'll assume the observer knows the laws of nature, but has no knowledge of the state of the universe, except whatever is gleaned from observation. The second part fits our situation in the universe, but the first does not, since in the last few centuries we've been using our observations to learn the laws of nature as well as learning the state of the universe. I make the first assumption partly because it would be much harder to model an observer who's trying to learn the laws of nature. But there's another reason, which is that I would like to understand the Gibbons-Hawking entropy of the cosmological horizon. And I believe to do that, this is the correct model. So the algebra I will define will depend on the laws of nature, but it's required to be both universal and background independent, meaning it's defined once and for all without any knowledge of the specific spacetime in which the observer is living. Now, I'm going to list some relevant papers, but I don't have time to describe what's in them. I'll just say that the starting point for what I'll talk about was trying to generalize the construction in this paper. And I haven't listed it, but there's a paper with the same title as the lecture, which was my attempt to generalize this construction. Now, we expect that in a full theory of quantum gravity, an observer cannot be introduced from outside, but must be described by the theory. What it means to assume the presence of an observer is that we define an algebra that makes sense in a subspace of states in which an observer is present. We don't try to define an algebra that makes sense in all states. First, let's describe the situation in the absence of gravity. The observer, for simplicity, I'll assume the observer propagates on a geodesic in spacetime. I could instead consider, for example, an electrically charged observer whose motion is affected by ambient electric fields or electromagnetic fields, or I could equip the observer with a rocket ship. But for the simplest model, I minimally couple the observer to gravity and the observer travels on a geodesic. For example, the role of the observer could be played by our civilization here on planet Earth, and the Earth is moving on a geodesic to a good approximation. Though if you wanted to be more precise, you would take account of the spin of the Earth, the rotation of the Earth, and its effects on the motion. So then we parameterize the observer's worldline by proper time tau. Then, as in classic work of Unruh, I'm not certain if it's the first reference, but anyway, going back at least as far as Unruh, one makes a simple model where the observer measures along gamma, for example, a scalar field, or other quantum fields such as the electromagnetic field or the Riemann tensor, and also their covariant derivatives in normal directions. I don't include the covariant derivative along the world line because the observer already is measuring phi and other fields at an arbitrary time tau. So the tau derivatives would add nothing new, but it is important to allow the normal derivatives to the world line. Now, an elementary but not so well-known point is that smearing a local field phi along a time-like curve is indeed sufficient to define an operator. And since this isn't so well known, I'm going to spend a few minutes to explain it. But because it is true, there does rigorously exist an algebra of operators defined by smearing along the observer's world line. By contrast, smearing in space does not define an operator unless phi has rather low dimension. An important special case of this is that it's not possible to define an operator by smearing a local field on a cut of a black hole or cosmological horizon, or even on the whole horizon. I'll take a moment to explain this. Unfortunately, the top line is cut off. I'm not exactly sure why that happened. First, the reason that some kind of smearing is necessary is the following. Now it's okay. Now you can see the top line, I think. If omega is a Hilbert space state, for example, the vacuum, and 5x is a local operator, then 5x acting on omega is never a Hilbert space state because its norm is infinite. Its norm would be given by this expression, but that's the limit as y goes to x of the two-point function, which is always infinite. Now we should ask, does smearing in space help? Well, if we smear in d spatial dimension, we find the following. Let f of x be a smearing function, a smooth function of compact support, and let phi sub f be phi smeared with f. Then we compute the norm of phi sub f, and we find this expression. Now, if phi has dimension delta as measured in the ultraviolet, then the two-point function of phi dagger phi goes as 1 over x minus y to the 2 delta plus less singular terms. And then the integral converges only if 2 delta is less than d. So for example, in QCD, the space dimension is 3. So little d would be 3 at most. And the lowest dimension operator in QCD with the gauge invariant operator with the quark bilinear q bar q with delta equals 3. So the inequality 2 delta less than d isn't satisfied. And therefore, QCD is a simple example of a theory in which no operator can be defined by smearing in spatial directions. And by the way, going to Euclidean space doesn't help. Then little d could be 4, but the inequality is still violated in the case of QCD. However, smearing in time does make a true operator regardless of the value of delta. The Feynman I epsilon is crucial. In Minkowski's signature, in Lorentz signature, at fixed space but different times, the OP reads like so. It's important that it's not t minus t prime to the minus 2 delta, but there's a minus I epsilon. And now, if we take a smearing function that depends only on the time, so f is a smearing function, f of t, of, again, a smooth function of compact support. But at a fixed spatial position, we smear only in time to get this expression. And do the same calculation as before, we find that the norm of the state phi f of x acting on the vacuum, well, first of all, it's given by this integral, plus terms that are less singular from higher order terms in the OPE. And the less singular, these terms are less singular but similar. They all have the Feynman I epsilon, so they all get treated in the same way. The integral is clearly convergent if epsilon is positive, and I claim that it is finite also as epsilon goes to 0. To prove that, we just essentially integrate by parts. We first observe that t minus t prime minus I epsilon to a power is the nth derivative for any n of the same thing to a bigger power times a constant. So the integral we want can be rewritten this way. And then we can integrate by parts n times. So it's equal to this. And since f was smooth, there's no problem with the derivatives. And since f had compact support, there are no surface terms when we integrate. And for large enough n, it's obvious that the integral converges. So it's possible to define an algebra of operators smeared along a time-like worldline. If that had not been true, then it would have been too much of an idealization to think of the observer as being point-like, living along a geodesic. We'd have needed to smear the observer in space to make a sensible algebra, but that's not necessary because of what I've just explained. Well, what is the algebra of such operators? This question is answered by the time-like tube theorem, which is a close cousin of what in ADS-CFT duality is called HKLL reconstruction. The time-like tube theorem says that in quantum field theory without gravity, the algebra of operators along a time-like worldline is equivalent to the algebra of operators in a certain open set E of gamma. So here I've drawn in blue a worldline that has initial and final points. And roughly E of gamma, well, E of gamma consists of all points you can reach by deforming this world line through time-like curves, keeping fixed its endpoints. So in Minkowski space, if gamma is the indicated blue curve, if gamma would be the corresponding causal diamond. The important thing is that the algebra of a world line is actually the algebra of a space-time region. So you see, that means this is a theorem in ordinary quantum field theory. So in ordinary quantum field theory, you can equally talk about the algebra of a world line or the algebra of a space-time region. But when we go to gravity, the algebra of the world line is going to be well defined, and the algebra of a region would generally be problematical. So I claim that the algebra of the world line is a better notion for generalizing to gravity. So without gravity, A of gamma is the same as the algebra of operators in a certain open set. But it appears to make more sense when gravity is included. So we use it as a reasonable substitute for what we do in ordinary quantum field theory without gravity. Now, to understand more concretely what is A of gamma in the presence of gravity, let's focus on a particular observable. For example, we have a scalar field phi, and we evaluated it. Well, x of tau is the observer's position at proper time tau. The observer's position in space-time at proper time tau, and then phi of x of tau would be a typical observable, roughly speaking. We'll have to correct it a bit, but I'll abbreviate it just as phi of tau. So phi of tau is the value of phi the observer measures at proper time tau. So without gravity, phi of tau would be a good observable, except we have to smear it in tau to get a Hilbert space operator. When we take gravity to be dynamical, we have to consider that the same world line can be embedded in a given space-time in different ways, differing by constant shifts of tau. So here's the world line. Along a time-like world line of an observer, there's a natural notion of proper time differences between 2 points. But there's no natural notion of the absolute proper time. So if I tell the observer to make a measurement when the proper time is 3, that's not meaningful. It is meaningful, having made one measurement, to make another measurement a proper time 3 seconds later. But it's not meaningful to say that we're going to make the measurement when the proper time is 3 seconds. Only proper time differences are meaningful. So 5 tau by itself isn't a meaningful observable in the context of gravity. We need to introduce the observer's degrees of freedom and define tau relative to the observer's clock. In a minimal model of the observer, we give the observer a Hamiltonian, which will be mc squared plus q, and I'll let p be minus id by dq. However, it turns out that it's better to assume the observer energy is bounded below, so I'll take q to be non-negative. That ensures that m actually is the observer's rest mass. We then only allow operators that preserve the condition that q is non-negative. So for example, we don't allow e to the minus ip, which would not preserve that condition. We replace any operator by what we get by projecting it before and after onto states of non-negative q. So for example, if theta of q, or which I'll call pi, is the projection operator onto non-negative q, we replace e to the minus ip with pi e to the minus ip times pi, and we make a similar projection for any operator. We now want to allow only operators that commute with the gravitational constraint operator, which will be the sum of the observer Hamiltonian with any gravitational constraint operator that generates a shift of tau along the world line. To explain this better, let me remind you that when we do gravity, we have to impose constraints that represent diffeomorphism invariance. I imagine first imposing all the constraints away from the observer's world line. Let's assume that's already been done, and we work in a Hilbert space where that's been done. We still have to impose a constraint that shifts the observer proper time by a constant, and such an operator will act on both the bulk fields and on the observer degrees of freedom. So H bulk is the bulk part of that constraint, H observer is the observer part of that constraint. So this is the final constraint operator we impose after imposing all other constraints. It's the constraint operator that shifts the observer, the proper time measured by the observer's clock, while also making a compensating shift of all the bulk fields. So an operator that commutes with h hat is invariant under a spacetime diffeomorphism that moves the observer worldline forward in time together with the time translation of the observer system. Well, how do we find operators that commute with this constraint? Since the bulk operator, by definition, is moving tau forward in time, its commutator with 5 tau is minus I phi dot. So what we need, since the observer Hamiltonian is a C number plus Q. So in order for h hat to commute with an operator, such as 5 tau, we would need Q commuted with 5 tau to be the opposite, equal and opposite to this. So we would need 5 tau to have this property. But we can achieve that by just setting tau equal to P, where P is the canonical conjugate to Q, because Q acts as ID by dP. Or more generally, we could pick a constant S and say that tau is P plus S. So a typical allowed operator is 5P plus S, or more precisely, we have to act with the projection operator pi before and after. So the typical allowed operator is pi times 5P plus S times pi, which I'll call phi hat sub S. And in more detail, it's like this. Now, in addition to these operators, with phi possibly replaced by any local field along the world line, such as the electromagnetic field or the Riemann tensor, there's one more operator that commutes with h hat, namely Q itself. Because h hat was bulk operators plus a C number plus Q, so it commutes with Q. So we define an algebra, which I call the observer algebra, A sub observer, that's generated by the phi hat S as well as Q. Now, what I've done hopefully sounds background independent, because I described it without telling you anything about what the background was. But background independence really depends on interpreting the formulas properly. If we think that phi hat S is supposed to be a Hilbert space operator, we won't have background independence. Because to get a Hilbert space on which phi hat S could act, we would have to pick a spacetime M in which the observer is propagating. Then we won't have background independence. The definitions will depend on M. We have to interpret phi hat S in a way that doesn't depend on the spacetime in order to make the algebra background independent. We have to think of the observer algebra as an operator product algebra rather than an algebra of Hilbert space operators. The algebras for different M's are inequivalent representations then of the same underlying operator product algebra. In the absence of gravity, well, okay. Excuse me. In the absence of gravity, Holland and Wold did something somewhat similar. And they were trying to explain what it meant to consider the same quantum field theory in a different spacetime. And in order to capture that idea, if you try to talk about Hilbert space operators and their commutation relations, you'll have trouble. But if you talk about OPE, the operator product expansion, it can be defined universally independent of the spacetime, provided you allow the coefficients to depend on the Riemann tensor and its derivatives. So here I'm doing something similar. In the absence of gravity, we'd characterize the objects 5 tau by their universal short distance singularities. For example, the leading term in the OPE is what I already wrote before, but we would consider all terms of all orders in the OPE. That characterization does not require any knowledge about the quantum state or the spacetime the observer lives in. After coupling to gravity and including the observer and the constraint, the short distance expansion in powers of tau minus tau prime becomes an expansion in 1 over q. Then we characterize the observer algebra purely by the universal short distance or 1 over q expansion of operator products. So phi is a symbol for which we give a short distance expansion. It's not a Hilbert space operator at this stage. With that understanding, A sub observer is background independent. Now, there's a very special case of a background that turns out to be important. That's the case that M, the spacetime, is an empty de Sitter space with some positive value of the effective cosmological constant. So I've written the Penrose diagram here. As usual, the Penrose diagram is drawn to show only two coordinates, time and a space coordinate. Time runs vertically in the picture, and space runs from left to right. Actually, in de Sitter space, time goes from minus infinity to plus infinity. So the blue lines at the top and bottom represent the infinite past and the infinite future, projected to finite times by the conformal mapping used in drawing the Penrose diagram. Space in de Sitter space is a sphere, and what's been drawn, if you like, is the latitude of the sphere, with the south pole on the left edge and the north pole on the right edge. The polar angles other than the latitude are suppressed in drawing the diagram. The south pole is a geodesic. The south pole at all times, an observer who sits at the south pole at all times is propagating on a geodesic, and using the symmetries of de Sitter space, any geodesic is equivalent to that one. So we can assume our geodesic observer is living on the left edge of the diagram. The observer then has a past horizon, this diagonal line, and a future horizon, which is this diagonal line. Remember that Penrose diagrams are usually drawn so that a causal curve propagates at most at a pi/4 angle from the vertical. So what's to the right of this diagonal line is forever out of the observer's vision, and what's to the past of this diagonal line is out of the observer's reach, is what the observer can't influence. The green region is called a static patch because it's invariant under a particular de Sitter generator H that advances the proper time of the observer. In the absence of gravity, there's a distinguished de Sitter invariant state, often called the Bunch-Davy state, but I'll just call it psi ds, such that correlation functions in this state are thermal at the de Sitter temperature, 1 over beta ds. Beta is 2 pi times the radius of curvature of de Sitter space. Now, for example, this thermality of de Sitter space for the 2-point, endpoint functions for all n are thermal, but I'll just state what thermality means for the 2-point function. For the 2-point function, it means that there are two key properties. The first is time translation symmetry. So if you shift the time of both operators by a constant, you have two operators along the world line at different times. You shift the times, but keeping the time separation constant. The 2-point function along the world line in the de Sitter invariant state is a constant because the state is de Sitter invariant. The second property is roughly periodicity in imaginary time, because thermal correlation functions, roughly speaking, are periodic in imaginary time. But for operators along a world line, the precise statement of that is more subtle. The precise statement is the KMS condition, which says that if you shift the imaginary time of one operator by minus I beta, that's equivalent to reversing the order in which the two operators are multiplied. To state it more accurately, the 2-point function is holomorphic in a strip, and the boundary values on the two edges of the strip are the correlators in opposite orders. Now, when we include gravity in the observer, so without gravity, we have this Bunch-Davy state psi ds. When we include the observer, I define a special state in which the observer has a thermal distribution at the de Sitter temperature. To e to the minus beta q, because you have to square the wave function that gets rid of the 2. And this is a normalization factor to make the state normalized. Then, going to gravity, we replace 5 tau by its gravitationally dressed friend, where we replace 5 tau by phi of p plus s, and project before and after on the constraint that Q is positive. Then a straightforward computation. I'm not going to show you this computation, but I promise you it's an elementary and straightforward computation that only involves contour deformation. If you want to see the computation, you can look at the paper that has the same title as this lecture. First, the first fact is more obvious that we still have time translation symmetry, but time translation symmetry is now obvious. But what's not obvious, and is actually rather deep and surprising, is what happens to the KMS condition. The KMS condition does not say that the two operators commute, even for their matrix element. It says that they can, if you shift the proper time of one of them by minus I beta, you can reverse the order of the two operators. After you include the observer and put the observer in this particular thermal state, you find that the KMS condition simplifies and involves no shift of imaginary time. So the KMS condition now reduces to the statement that for computing expectation values in this state, you can reverse the order of the two operators. So the modified KMS condition tells us that if A is an element of the observer algebra, and we define the trace of A to be the expectation value of A in the state psi max, then the function trace does have the algebraic property of a trace. The trace of AB equals the trace of BA for any A and B in the observer algebra. The function also has the property that the trace of A dagger A is positive for all non-zero A, meaning in particular that it's non-degenerate. And moreover, assuming we had normalized the de Sitter invariant state, then psi max is normalized. So the expectation value in the state psi max of the operator 1 is 1, and thus the trace of 1 is 1. Now let HDS be the Hilbert space we get by quantizing fields in de Sitter space in perturbation theory. So HDS describes states with any number of graviton excitations, but not with the number of graviton excitations of order 1 over H bar. That wouldn't be in the standard perturbative Hilbert space. An H bar independent number of graviton excitations produces a back reaction on the geometry that's of order G. So HDS describes states with an order 1 change in the geometry, with an order G change in the geometry, not with an order 1 change in the geometry. If you want to consider states with an order 1 change in the geometry, you need to do something sophisticated, more sophisticated than I'll describe. Now let psi be any state in this perturbative Hilbert space and consider the function that takes an operator to its expectation value in that state. Roughly speaking, because the observer algebra has a non-degenerate trace, which I've denoted as trace, we can hope there's a density matrix, rho, in the algebra, such that the expectation value of an operator in the state psi would be the trace of A times the density matrix. Rather, as in ordinary quantum mechanics, we expect the density matrix to be a positive element of the algebra with trace 1. For example, let's find the density matrix of the state psi max. The definition of the trace makes clear the answer. The density matrix of the state psi max is sigma max equals 1, because the condition we're supposed to satisfy is that the expectation value in a state psi max of an operator A, we're supposed to find a sigma max such that this is true. But the definition of the trace of A times sigma max is the expectation value of A times sigma max in the state psi max. So we're trying to make this equal to this. And the operator that does that is clearly sigma max equals 1. That means that psi max is a state whose density matrix is 1. In ordinary quantum mechanics, a state whose density matrix is a multiple of the identity is called a maximally mixed state. And so this is telling us that psi max is the analog in de Sitter space with gravity of a maximally mixed state in ordinary quantum mechanics. In ordinary quantum mechanics, we usually normalize the trace so that the trace of the identity is the dimension of the Hilbert space. And that's why the density matrix of the maximum mixed state is a multiple of the identity, not the identity itself. Here, the dimension of the Hilbert space was infinite, so we couldn't make the trace of the identity the dimension of the Hilbert space. Instead, we arbitrarily normalized it to be 1. And that's why the density matrix of the maximum mixed state is 1 rather than a multiple of 1. So we found the density matrix of one state. Now I'm going to find for you the density matrices of a lot of states, in fact, a dense set of states. If A is any operator in the observer algebra, consider the state psi A, which is A times psi max. I claim its density matrix is A dagger, because if we take any B in the observer algebra, the expectation value of B in the state psi A, since this is psi A, can be written this way. And by definition, that's the trace of A dagger BA. And because of the cyclic property of the trace, that's equal to this. But the equality of this and this tells us that A dagger is indeed the density matrix of the state psi A. So we found the density matrix of the state psi A for any state that the observer can make by acting with any operator on the state psi max. But the states psi A are dense in the perturbative Hilbert space roughly by the Riesz-Leiter theorem, which is the fundamental result about entanglement in quantum field theory. So a dense set of states have density matrices. If we want all states to have density matrices, we need to take a useful further step. The Hilbert space HDS is the closure of a dense set of states of the form A times psi ds. So if we want every state in H to have a density matrix, we have to similarly take a closure of A. In other words, we found density matrices for a dense set of states, but the Hilbert space is the closure of the dense set of states. So if we want to have enough operators in ADS so that every state will have a density matrix, we have to take a closure of the observer algebra. This closure is no longer background independent. It can be defined as the von Neumann algebra generated by bounded operators in the observer algebra. I'll call it A observer comma ds to specify that once we took the closure, it does depend on the spacetime. So now it's true that every state in Hilbert space has the density matrix in the observer algebra. It's in this step and only in this step that we need to introduce von Neumann algebras. Now, what is it good for, what we've done? Let's recall that Bekenstein and Hawking discovered that one should attribute an entropy to a black hole horizon. And not too long after, Gibbons and Hawking suggested one should also attribute an entropy to a cosmological horizon, such as the horizon experienced by an observer in de Sitter space. So Gibbons and Hawking attributed an entropy to these past and future horizons and their intersection, which is this so-called bifurcate horizon. However, a microscopic interpretation of what's meant by the entropy of a cosmological horizon has been obscure, even compared to the black hole entropy, which we don't understand that well, but which we understand much better than we have understood the entropy of a cosmological horizon. We can now give at least a partial answer to this question, at least for the case of de Sitter space. Indeed, once we know that states have density matrices, we can define entropies as well. The von Neumann entropy of a density matrix is, as usual, minus the trace of rho log rho. And this definition makes sense in the present context because we have a trace and we have density matrices. In ordinary quantum mechanics, a maximally mixed state has a density matrix that's a multiple of the identity, and it has the maximum possible von Neumann entropy. The analog here is the state psi max, whose density matrix is sigma max equals 1. It's clear that the state with psi max has entropy 0 because the logarithm of 1 is 0. So minus the trace of rho log rho is 0 for rho equals 1. And by imitating an argument that in ordinary quantum mechanics proves that a maximally mixed state has maximum possible entropy, one can prove that every other density matrix other than 1 has strictly smaller entropy. I'll give one version of the proof here, very briefly. Let rho be any density matrix other than the identity. Then if if t is between 0 and 1, then rho sub t, which is 1 minus t plus t rho, is a positive matrix of trace 1, so it's also a density matrix. Let f of t be the entropy of rho t, which is minus the trace of rho t log rho t. So S of rho, which we'd like to show is negative, is f of 1. Well, it's obvious that f of 0 is 0 because f of 0 involves the logarithm of 1 again. And it's easy to prove that f prime of 0 is 0. Just from the definition of rho, you can, not too much difficulty to see that. And it's also true that f double prime of t is negative. That's less obvious. To prove it, I use this representation of the logarithm of an operator, and then we can compute that f double prime of t is given by this expression, and that's minus an integral of the trace of a Hermitian operator, this self-adjoint operator. So since f prime of 0 is 0, f of 0 is 0, and f double prime is negative, we get f of 1 negative. So S of rho is negative. So we've discovered that the thermal state, which had entropy 0, has bigger entropy than any other state. We found that the system consisting of an observer in a static patch in de Sitter space has a state of maximum entropy consisting of empty de Sitter space with a thermal distribution of the observer energy. Why did this happen? The original argument that empty de Sitter space has maximum entropy goes back to Busso, who argued it must be true based on the second law of thermodynamics, because the static patch is empty in the far future. If you have a particle, or in the static patch, unless it's with probability 0, it might be perfectly aimed at this upper left corner of the diagram. But with probability 1, it will leave the static patch through the future horizon somewhere. So in Busso's discussion, there was no observer, but with probability 1, the static patch was empty in the far future. And then Busso said that since the static patch is spontaneously evolving to be empty, and we know that the evolution of an isolated system tends toward maximum entropy, it must be that the empty static patch has maximum entropy. Now, in the present context, we've defined the static patch by the presence of the observer. So by definition, the observer doesn't leave the static patch even in the far future. But we can expect that in the far future, the static patch is empty except for the presence of the observer, and that the observer will be in thermal equilibrium with the bulk quantum fields. And that's what we see in the state psi max. So adapting Busso's argument to the presence of the observer, we would predict that psi max would be a state of maximum entropy, which indeed is what we found. Now, Busso's argument was based purely on thermodynamic reasoning with no microscopic definition of entropy. What we've gained here is that we do have a microscopic definition of entropy. And so we proved microscopically that the state psi max does have maximum entropy as suggested by the thermodynamic argument. A price we pay though, to Gibbons and Hawking, the entropy of the static patch is supposed to be A over 4G, where A is the area of the horizon. And in my presentation, the maximum entropy is 0 rather than A over 4G. The reason that happened was that we didn't have a good motivation for how to normalize the trace operator. And since we didn't, we just normalized it so the trace of the identity was 1. if you follow through the definitions, you'll see that if you used a different value of the trace of the identity, you'd get a different constant value for the maximum entropy. It would shift all entropies by constant. So the trace of the identity was naturally infinite because the Hilbert space had infinite dimension. And so there was a renormalization involved in taking the trace of the identity to be one. So we made an additive renormalization of all entropies, shifting all entropies by a constant amount. And since we didn't have a good motivation to do otherwise, we chose the additive renormalization to make the maximum entropy zero. In this derivation, the numerical value of the maximum entropy was an arbitrary constant, which we just set to zero. Now, in a more general spacetime, I don't know an equally explicit definition of the entropy of state of the observer algebra. But there's a fairly reasonable conjecture, which is inspired by Aaron Wall's proof of the generalized second law, and has some support from recent work of Chen and Pennington, and also some support by a paper that appeared on the arXiv last night, as I'll mention later. This conjecture was stated in my paper, the paper with the same title as the lecture, but without very much evidence for it. The idea is to interpret the Hartle-Hawking no-boundary state as a sort of universal state of maximum entropy, generalizing empty de Sitter space, which has maximum entropy among states in a particular de Sitter spacetime. The expectation value in the no-boundary state, so I'll call the no-boundary state psi HH, that's a state of the observer algebra, and I'll denote it as sigma, or as the expectation value for an operator A, I'll call sigma of A. Then if A going to rho of A is any state of the observer algebra, then I suggest that the relative entropy between rho and sigma gives, up to sign, a definition of the entropy of the state seen by the observer. So that's my conjecture for a general definition of entropy in the context of cosmology. Here it's important that we do not try to normalize the no-boundary state. Rather, we just take it as it appears from the gravitational path integral. This statement is actually a slight improvement from what I wrote in the paper. When I wrote in the paper, I tried to imagine normalizing the no-boundary state. A heuristic explanation of why not to normalize it is that the observer has no idea how to normalize it, because the normalization is probably dominated by the no-boundary state in some other spacetime that the observer isn't living in. Anyway, if we don't normalize the no-boundary state, but just take it from the path integral, it gives correctly the A over 4G term in the entropy. That's because, roughly, the no-boundary state in a given de Sitter spacetime is proportional to e to the A over 4G. And if you work through the definition of relative entropy, the logarithm of that e to the A over 4G will appear as a constant term in the entropy. So the maximum entropy would be zero if we normalized the no-boundary state to have norm 1 in the observer's spacetime. But if we take it from the path integral, we get what Gibbons-Hawking regarded as the natural entropy of the de Sitter of the static patch. So, well, at least, well, as of when I was writing these slides, the main evidence for the proposal is that in the case of de Sitter-like spacetime, it gives correctly the A over 4G term of the entropy. And if you have a landscape of de Sitter vacua, it gives the appropriate A over 4G in each one. That statement is a reinterpretation of the original calculation of Gibbons and Hawking. Beyond this, and apart from the analogy with the work of Aaron Wall, the main appeal of the proposal is that it makes sense universally as a definition of entropy in a cosmological setting. Well, I wrote those slides a couple of days ago, but as I say, there's a paper on the arXiv last night by Kudler-Flamm, by Blomart, Kudler-Flamm, and Urbach, who give some additional evidence. The proposal only makes sense if it's true that the no-boundary state is tracial for the observer algebra. So, well, I wrote the other day that it wasn't clear why this is the case in a general spacetime, although I proved it for you in the case of the static patch in de Sitter space. There is some more evidence for this in the recent paper. Okay. I should explain though why the proposal only makes sense if this is true. Well, that would be true in ordinary quantum mechanics. In ordinary quantum mechanics, this formula for the entropy gives the standard answer if sigma is the identity. If sigma is a multiple of the identity, it gives the standard answer up to an additive constant that is independent of rho. But if sigma being tracial means that sigma is a multiple of the identity. If sigma isn't a multiple of the identity, this formula is definitely wrong in ordinary quantum mechanics. So we shouldn't expect it to be right in cosmology. So part of the conjecture is that the no boundary state is tracial for the observer algebra. Now, another remark I want to make here is that we made the idealization of assuming the observer lives forever. And we also made the idealization of assuming the observer can make arbitrary measurements along the world line. These are not realistic assumptions. For example, they don't apply to us. But I suspect we need to make these idealizations if we want to get the Bekenstein-Gibbons-Hawking entropy as the entropy of a state of the observer algebra. In other words, if we want the entropy to be the area over 4G plus quantum corrections, I believe we need these idealizations. If we entropy means information that could be obtained in principle about the state, but hasn't been obtained. So to the extent that we make a more realistic model of the observer, we'll make the entropy smaller, and how much smaller it will be will depend on precisely what model we assume for the observer. So the only way to get a universal answer is to idealize the situation and assume the observer can do everything. Now, there are a lot of things missing in this presentation. For example, what about an observer or a civilization that did not always exist or will not always exist? I used a field theory language. Can we generalize the discussion to string/M theory? Though the definitions make sense in any space-time, I want to remark that the discussion is most interesting for an observer who, because of black hole or cosmological horizons, cannot see the whole universe. I think interesting is a better word here than natural. And finally, is it possible to justify the proposal that I stated at the end for a general definition of entropy in a cosmological setting? Thank you. This is what I have to offer today.
Thanks very much, Witten. So there were many questions during the talk. So I think the best way perhaps is to invite those who ask questions to unmute themselves. Let me ask with Amer. Let me find you and ask you to unmute you. Here you are. So I'll ask Amer to unmute and he can probably ask his question.
Okay, thanks, Carlos. Hi, Edward. Nice to see you. So one question I have is, well, I think you answered one of the questions, but one question I have, you said, should one assume that the word line, well, why don't we consider other diffeomorphisms of the observer's word line? That's one question I had.
I'll answer also your first question, though, even though I'll comment on it. As you said, should we assume the world line extends to the infinite past and infinite future? I believe the answer is yes if we want to get the Gibbons-Hawking entropy. But I think it would be very interesting to understand what's a good way of thinking about an observer who's more restricted. So I didn't mean to imply at the end that more realistic models aren't interesting, only that I think it might be this is the model that gives the Gibbons-Hawking entropy. Then you asked, should we consider other diffeomorphisms? Well, we could, if we want to. See, if we want to, we should pick I said the observer has a well-defined proper time up to a constant shift. If we want another version would be to say that there's an arbitrary metric along the observer world line, and we gauge fix that to be 1.
Mhm.
And I've already done the partial gauge fixing
Okay.
before starting the lecture.
I see.
So there would be a formalism where we would make arbitrary diffeomorphisms of the world line, but then we would quickly reduce it to the case I considered.
Okay.
I think the constraint I considered is actually the important one.
Okay. So another question I have is in I just wanted to make sure because I was a bit confused. So in quantum field theory,
Yes.
we cannot define I think that statement is true, correct me if I'm wrong. The central operators that they can commute on the bifurcated horizon that can commute a lot. Would operators defined on the left and right wedges of the Penrose diagram? So are we saying something different here?
There aren't
we
any
can.
operators on the bifurcate horizon
Mhm.
because I showed you that smearing in space only
Yeah.
works for operators of low dimension. So I'll say this in 3 dimensions. In 3 space dimensions. In
Mhm.
3 space, the same is true in every space dimension, but the numbers might be more familiar in 3 space dimensions. In 3 space, 4 space-time dimensions, the minimum dimension of a scalar field is 1 because of unitarity.
Yes. Mhm.
And our inequality would tell you that the dimension has to be less than 1 for smearing in 2 dimensions. 2 is the dimension of a slice of the
Right.
horizon
Mhm.
to make an operator. So in 3 space, 4 space-time dimensions, or in general, any dimension, smearing on a cut of the horizon doesn't define any operators. That's part of the consistency of ADS-CFT duality, because if you could make an operator smeared on the bifurcate horizon, it's at risk of being central, whereas in
Oh,
ADS-CFT,
I
it's
see.
obvious there aren't any such central operators.
Oh, I see. Okay. I think that
The world
okay.
would be
One.
completely different. Sorry. If you could make, if phi's on the horizon, if you could smear on the bifurcate horizon to make operators,
Right.
you'd have an infinite dimensional center because you could, well, I don't know what happened. Mathematics and physics would be completely different if you could do that. It would be very important if you could, but you can't.
I can't. Okay. So it's not okay. Like what I should.
Right.
I was going to follow what can we do it or is it like it's impossible. It's just
Yes,
cannot we
right.
cannot
That's
do it.
correct.
Okay, I see. So I guess one last question I have is well, this is more like you said, been thinking about generalizes to string theory and M theory. Yep, I guess one major issue one has to make sense of is the notion of a region, subregion, boundary, and of course locality, because the string has an the extended nature of the string. I mean, these things. I'm not sure if you have any thoughts on this.
Well,
To
I don't know the best way to think about what I've said in the context of string theory.
okay, okay, okay. Maybe we'll. Okay. Well, thanks for
Sure.
thanks for the answers.
There was, sorry,
Shall
please.
we take the questions in order in the chat, or?
Yeah. We can go like that. So I asked Gopal to unmute because he had a question about multiple observers. Are you there, Gopal? Okay, I don't see him.
Well, I can raise the question.
Yeah.
The question was,
Please.
is it sufficient to consider a single observer? What if there are multiple observers? Well, observers who are in communication with each other might as well be treated as one observer from the point of view of the lecture. But observers, for example, in de Sitter space, who eventually are outside, okay. Observers who are not in communication with each other, from the point of view of any one, the other one is just part of the matter which is being observed.
Mm.
So, for example, there might be a civilization on Alpha Centauri for all we know, but
Right.
from our point of view, that's part of the solar system in Alpha Centauri.
I see. There was then a more mathematically sided question by Ulrich Penning. Can you see it there, or we ask?
Yes, I see it. Yes. So Ulrich Penning asks, what's the type of the von Neumann algebra that we get by taking the closure of the observer algebra? Well, in de Sitter space, it was type 2 because it had a trace where the trace of the identity could be normalized and it was finite. And the only type of von Neumann algebra that does that is type 2-1, actually. So it was a type 2-1 algebra. In the presence of a black hole, you can get a type 2 infinity algebra. For an observer who can see the whole universe, or more exactly, who can see a whole initial value surface, one would expect the algebra to be of type 1. I didn't prove in general that there's a trace. That was only a conjecture that the no boundary state is tracial. But if it's true that the no boundary state is tracial, that means that the observer algebra is always type 1 or type 2. And one expects it to be type 1 or type 2, depending on whether the observer can or cannot see a whole initial value surface in spacetime.
And then after that, there was a very nice experimental side question by Giorgio Torrieri. Giorgio, if you want.
Sure. Your main motivation was cosmology, but you might be aware of experimental proposals which apparently are feasible within our lifetime to observe gravitational effects on entanglement of nanoparticles and so prove the quantization of gravity this way.
I think that claim is too optimistic. Could you send me by email the best reference to these experiments?
Of course. It's called the Bose-Marletto-Vedral experiment in the literature. I will. Yes, I was curious to know if this kind of algebra would have an effect, but yes, of course I will.
Well, I expect it will not have an effect, but also I expect that the claim is too optimistic.
There was a further question by Amr, but then I think he already asked and you already answered.
Okay.
Prem, is there any question there in the lecture room?
I have a question, unless somebody else.
Well, go ahead if you have a question.
Okay, I was wondering about the similar algebra for antidecitor space, because there's a natural algebra of operators at the boundary, single trace operators, multi-trace operators. Does that then allow us to define, think of a notion of entropy or black hole entropy for antidecitor black holes?
Yes, but that would not be a new observation. That would just be the entropy defined in the boundary CFT. Okay. Sorry, I'm being a little bit too flippant. Okay. There is a story somewhat similar to what I explained in the field of an antidecitor black or Minkowski's asymptotically flat black hole. Some of the papers that at the beginning when I had a list of papers, some of the ones at the top were on black holes in asymptotically flat or asymptotically antidecitor spacetime. But the quickest answer to your question is what I said, that entropy defined in the boundary CFT is believed to be the Gibbons-Hawking entropy of the black hole. But there is a story more similar to what I said. Leaving that remark aside, there's a story that is actually analogous to what I explained in the lecture. That constructs, in that case, an algebra of type 2 infinity, which is a kind of large n limit of the algebra you asked about. Yeah.
Thanks.
If there is any other question, please raise your hand with the React. Otherwise, we'll pass it to Prem and Gert to close. I think we pass it. Okay, Amr.
Amr has one more question.
Yeah, go for it. There you are.
Okay. You mentioned that in the Hilbert space, the number of graviton fluctuations in this construction, we need to do something more to make it vary as O to the 1 or something more sophisticated. And I was wondering if you can shed some light
Well, I don't think I can say anything useful, unfortunately. We can quantize around any classical solution,
Mhm.
and perturbably those will give different Hilbert spaces. Because if you quantize around the classical solution, the states you get will differ by an amount of order h bar from whatever you started with, but
Correct.
not by an amount of order 1. I don't feel that I don't personally feel I understand a good framework to quantize in a way that would let you see the small fluctuations about all classical solutions at once. So someone else might have a better understanding than I do, but I don't.
Thank you.
Thanks very much. Let me pass it on to Prem and Gert, who are going to say some closing words.
Yeah, thanks everyone. It's fallen on me to close this meeting. So for those who do not know me, I'm Gert Aarst. I'm head of the particle theory group in Swansea. But I'm standing here as a fellow of the Learned Society because, as Prem mentioned at the start of the talk, yesterday Witten was selected as honorary fellow of the Learned Society of Wales. So it's a great pleasure to congratulate him also from me. The Learned Society is like the Royal Society, except that the Royal Society is over 350 years old and the Learned Society is only 15 years old. So it's very young, but there's still a long time to go. And every so often, an honorary fellow of the Learned Society is also invited to give the David Olive lecture here. So that's a special, very nice combination to join those two events. And then finally, Prem mentioned the link between Ed and David Olive and Swansea, and I want to point out that it's not only for mathematical reasons that this link is important, but also for the tourist industry. Because when I moved to Swansea in 2004, I went in the bookstore in the US, and I'm trying to aim it, and I bought this travel guide. I hope you can see it, to hold it the right way. I bought this travel guide at Ohio State on Britain, and I look up Swansea, and there's a little box in there which is a fun fact, and it's called Brain Food, and it's very short, so I'll read it out loud. It says, one night in May 1988, Ed Witten, one of the world's leading mathematicians, was dining at Annie's, and for years the American had searched without success for a mathematical explanation of the makeup of knots. Suddenly jotting down a formula on a napkin, he rose to his feet and triumphantly announced, I've done it, I've cracked the theory of knots. And I'm sure this is exactly how it happened in real life.
We won't engage in any fact checking here.
So thanks again for the talk, and again, congratulations to the fellowship. And thanks everyone for joining in the room and also remotely. So
Well, let me thank again both the Learned Society and also the group here in Swansea for inviting me for this lecture, and finally the audience for your attention and the questions.
Thanks. Thank you. Thanks everyone. Thank you.